Okay, let's we get started here. So I'm going to continue with looking at problems in Lab 2. Lab 2 is due on Friday. And the next thing I want to talk about is the rand function, which you need, not that one, there it is. Exercise 3, random numbers. So there'll be several problems throughout the course where you need to use this rand function to get random numbers, or pseudo-random numbers. They're not true random numbers, but they look like random numbers. So I'll just start looking at this. Let me make a copy of an existing program. And we'll modify this copy.
God bless you. God bless you. Bless you.
I was just leaving his car.
Make sure.
I'm just going to get just a basic program running first, just to make sure that I've got my environment set up correctly. So this should just print OK. All right, there it is. Just to get that out of the way. I got the right header files in there. I can use cout. I can run the compiler. I've got my text editor opened up, ready to go. So just get those details out of the way. And now this problem here is to write a program that generates a list of 100 random integers. Well, let's start by solving a simpler problem. Let's just generate a single random integer.
We have to put this out.
Let's suppose we have an integer, call it, say, r, that's random. So we'll do something like this. So we'll declare r, we'll set it to 3 for now. It's not random, but we define an integer variable r, I'll just set it to 3, print it, and then I'm done. I suggest this at your level especially, of course at my level as well, it's at all levels. It's convenient to develop things incrementally, so just very small steps. All right. Although that's perhaps a matter of style. That's the style I advocate. All right, so now we could do either two things. Either we could look at the rand function or else add the code for the loop that does something 100 times. Which one should we do?
Rand function.
Okay, rand function, thanks. Rand function looks like that. We just call rand, and with opening and closing parentheses. This is called, here we're invoking a function, but it takes no arguments. This section in here is like an argument list. That's the syntax. We're invoking a function. Rand returns a value. That means it evaluates to a value, which then becomes the right-hand side of this assignment operation. This is an assignment operator, the assignment operator, or an assignment operator. I think there's some other ones. And so let's see what happens here. Does that look random? Doesn't look random anymore. Right? So what rand does is it gives you a sequence of pseudo-random numbers, but it gives you the same sequence every time unless you seed it differently. And we're just assuming, we're just using a default seed. I don't know what that seed value is, 0 or 1, whatever it is. And just to make my point a little bit more, I'm going to put a loop in here. Instead of 100, I'm going to just print 5. So let's have a loop that executes 5 times. This is the standard appearance or format of a loop that runs, a for loop that runs exactly 5 times. This would be the standard formulation. There are different formulations. For instance, I could have done this. We could start at 1 and stop when I exceeds 5. That's another way to do it. This would be equivalent. But in practice, you don't see this. You rarely see it. It works the same way. But people have standardized on this. And there's a good reason to standardize on this, because counting inside the computer starts at 0. In many situations, counting starts at 0. Offsets are based on 0. Addresses are based on 0. It has to do with the way RAM is accessed and manipulated. It turns out to be natural for a computing machine to start counting at 0. You know, when humans count, they start at 1. I count the people in the class. 1, 2, 3, 4. I don't do 0, 1, 2, 3. But that doesn't. When you start at 1, it's not as simple as starting at 0 internally when you're looking at the details of the computer. So that's the reason that this form has emerged as the standard form, but this would be equivalent. Let's get rid of that. So let's let's do it like this. So maybe a better way to do this, although I believe they're equivalent because the compiler is called optimizing. But here we declare R before we enter the loop, and we use the variable R inside the loop. So we declare a variable R, tell the compiler to allocate. So we want to allocate memory to store an integer. We'll use that memory here. So now we're inside a loop. We call this random function. We store the result in R. And then we print R. We do this 5 times. Oh, we better put a new line here. Otherwise, the digits will just be merged together. There it is, 5 random integers. But look, it's the same sequence. So we want to get a different sequence. So we use this function called srand. And we pass in a number, say 12. We're telling it, we're telling the random number generator, the pseudo random number generator. Remember, it's not true random numbers. And actually, that fact is important when you're dealing with security and cryptography. There's a critical need to have a good random number generator to properly accomplish security in computer networks. So that's why it's important always to remember that. So you wouldn't use this rand function, for instance, in the process of generating secret keys that are used for cryptography purposes, because it's too predictable. It's breakable. Anyway, for things like simulating random behavior, say like in a video game, like, oh, hey, sometimes the enemy fires a pistol, other times the enemy fires a ray gun, but we don't know, when he shoots one weapon or the other. That application of randomness, this function is sufficient for that.
So then you have to have C out and L twice in this?
C out twice?
Yeah, C out and L and then C out and L.
You don't have to have this, This is not necessary, but it does add an extra new line at the end. I'm not sure if it's worth doing that or not. Just take it out for now. That's just a formatting detail. So here we're saying seed the random number generator with 12. We need to compile. Let's see if we get a different sequence. We do. See that? But it's the same sequence. See, I took that new line out here, so I want to put it back in. It makes it a little easier to see the difference. So we're getting the same sequence because we're using the same seed. So we're getting the same sequence of integers. So every time we call rand, we say, give me the next item on that sequence of integers. So what the trick that is commonly done is to use something like, say, something that changes each time you run the program. And time called with the parameter 0 returns the number of seconds that have elapsed since some epoch, typically 1970, like the first second of 1970. So this will return the number of seconds that have elapsed since 1970. Now, if we run the program, very quickly within the span of a second, we might get the same sequence. Let's try that. Oh, and by the way, some compilers, this will compile. Let me see if it compiles with mine. See, I compile, but in the labs, I believe you're going to need to include this header. It's C standard live. So I'll put that in here just so that you see it. It's needed for some compilers. It's not needed for the one that I'm using, Xcode. But I believe it's needed in the lab. Maybe needed in Visual Studio. So let's see what happens. Oops, that's just a regular command. All right, let me run it. All right, 1287, 1288. Wow, that's very similar, actually. I was surprised you got the first 3 digits are the same on the first number. That's quite a coincidence. It does always seem to start with 12, though, doesn't it? It's a little flawed there, but it does give me different numbers. That's why, here's an example. You see, there's something that's being repeated there. It's random enough. Certainly for cryptography purposes, it wouldn't be random enough. Now, we don't want, if you look at the problem, the numbers are rather big. And so what's easier if we had smaller numbers. It doesn't matter, whatever the problem is. But here I think I'm asking for numbers between 0 and 100. Is that what I'm saying here? I don't say that, do I?
No, you say 100.
Just 100 random numbers. So that's good enough right there. Okay. But let me go another step. Let's suppose we want the numbers. Let's suppose we want the digits. We want the random numbers to be between 0 and 100. Then there's a trick there. We just take, we use this Modulo Operator. So this is called the Modulo Operator. It's a remainder operator. That's another word for it, remainder operator. It says, take the left-hand side, divide by the right-hand side, and just give me the remainder. Forget about the quotient. So 3 mod 2 would be 1, because 1 is the remainder. 5 mod 2 is 1. Because you take 2 2's out of 5, you're left with 1. You can't take any more whole 2's out of 5. You can only take 2 2's out of 5. So that's the remainder operator. And it is not working. Maybe I didn't save it. Oh, there we go. Now you don't see that pattern anymore. It's just, even looks more random this time. Suppose you want random digits, you want random digits between, say, 10 and 20. Well, it would be 10 plus rand 10. That'll return digits from 10 to 19 inclusive.
So do you want us to use SRAM on the homework or not?
Yeah, use SRAM.
So for Visual Studio basic Visual Studios, is it okay to use RAN or do you want SRAM?
No, it's RAN. SRAM is the same thing. It doesn't matter the compiler or the operating system. It's SRAM everywhere. Do you see this is RAND here? And this is SRAND here. They have two different functions. SRAND seeds the random number generator. RAND asks the random number generator to give us the next random integer. So they're related functions. They're different. Does that make sense? Okay. All right, so what else, what are we supposed to do here? So sequence, yeah, here's SRAND here. There it is. This is the time 0. Oh, and save the results to a file. So you can see here, we have, these are the files in the file system. Now if we run a.out, and we can tell it to, rather than using the console as a standard output stream, let's use a file as a standard output stream. So this is called a redirection operator. This is not a C++ operator. This is an operator that's given at the command line. So you see, nothing was displayed on the console because the output of a.out went into the file rather than the console. So there it is. Numbers.txt. There are the random numbers. Of course, now we want 100. And we'll just do normal random numbers like this. This would be what you need to do for the assignment. So there it is, 100 of these. I do colon 100. That means to jump to line 100. It's very convenient in BI. You can go to any line number like this. So go to line 100, and you see there's nothing below it. Well, there's a blank line there. I want to go to line 50. That's in the middle. It's colon 50. It's kind of convenient. I don't know how to do that with Nano. It might be possible, but I'm not sure. All right, we looked at quite a bit of these already. Are there any questions about these problems here? Is there anything in here that doesn't, did we talk about? We didn't talk about this yet, did we? Okay, let's do that. I'll call this inc because we're going to look at the increment operator. Let's declare an integer I and set it equal to 0. And then in here, let's use this increment operator. We'll do it like this, actually. Maybe this make it plus plus I, then we print I. No, I changed my mind about that. Let's show this. What is this going to print?
1.
Good. Let's verify that. Prints 1. Good. This will print 1, 1.
2.
Oh, 2. Sorry. 1, 2. Got that wrong. Good. Got me on that one. Very good. So, what about I think what I wanted to do was this. I'm going to use J. This is what I intended to do. And I'll just split them up a little bit so we can. So I want to compare. These are identical now. Initialize I to 0, increment I, print it. Initialize J to 0, increment J, print it. Okay, these are identical, except the variable names are different. This should be 1, 1. This is what I wanted. That's 1, 1. Okay. What about this?
1, 0.
Good. Everybody get it?
Pulse
1,
incrementer.
0. Because this is called a post increment, which means use J in the expression in which it appears, and then increment it afterwards. So to use J within the expression in which it appears, we would send the value of J into the output stream. So that would be 0. We're sending a 0 into the output stream. Now that we're done using J within the expression in which it appears, then we increment J. And wait a second. Before I do that, let's just verify that. There it is, 1, 0. Okay, that's what we were talking about. So after this, when we print I, what will this print? This is here. This is 1.
1,
1, 1. Okay. What does this print? 0, 1. Everybody get that? This prints 1, 1. Now this one prints 0, 1. Because here, the increment of J occurs after it's used in that output operation. So when we get to the next statement, J has been incremented. So the incrementing of J is done sort of between this output operation and the next statement. But here, the post increment is done immediately. Before it has very high precedence. It's evaluated before anything else. Let's take a look at that, that table. Operator precedence. Precedent, look at increment, it's at the very top. It's in the top slot there, precedence 1. It's very high level. Oh, it's the suffix postfix. This is, you know, I can't explain this. They don't distinguish. This is the prefix increment. Oh, I see, this is the suffix increment. Oh, I see, it's low level, so precedence of 1 is a low level, so it gets higher precedence as you go up. Okay. Oh no, that is not, I'm not right. This is the postfix. And this is the prefix. Yeah, these are done before this division is done. So I don't quite understand why that appears in a table like that, but I'm not going to struggle with that. I'm going to move on here. All right, let's verify that we got this right. There it is, 1101. Everybody okay with this? All right, one more exercise on this, just to make sure that we got it. How about we define a k, and k will equal I plus plus 1. And then let's see out. Can you solve a problem like that? This is a type of problem that'll be on the exam. But can you solve that problem?
Seven, right?
7. Any other suggestions? I don't know. I don't know the answer. I didn't figure it out. I just say 7. Okay. 16? Oh. 40? 4? 7, 4, and 16. Oh, that's about 9. So. That's pretty random there. Let's see if we can reason through it. Okay, I'm going to now just try to reason through this. This is postfix. That means we're going to use the value of I first, and then we'll increment I.
Yeah,
So it's at
so
0
it says it's 0.
plus
0
1.
plus 1 is 1.
So k is
0 plus 1 is 1. Now hold on. So after this line is completed, k will equal what? 1.
I will equal 1.
And I will equal 1. There we go. After that line completes.
So
Now here, this is a pre-increment, right?
So I will equal 2 times 3, which is 6.
Yeah. So this has higher precedence than multiplication. Multiplication has higher precedence than addition. Addition has higher precedence than output operator. So we got to do this one first, then this one, then this one, then this one. So if we increment I turns to 2, right? And then 2 times 3, that would be 6, right? And then 6 plus k, well, k, we made a record of that because I forgot. 6 plus k would be 7. Anybody think it's not 7? It's your chance to be famous if you say it will not be 7, it will be 8. I run the program and it's 8. Wouldn't that be great? But no one thinks this. We think it's going to be 7, right? Well, we can relax because this is not the exam. So let's just try it. Go ahead.
So when we're here, like, even though the code technically isn't finished because we haven't gone through everything yet, we still increment the I to 1?
Wait, I don't understand that comment.
Okay, because I is technically 0 at first.
I is 0 at first, correct.
And then K is I post increment plus 1.
Yeah.
So that's how we got K equals 1, because I
Yeah, and it is also how I became 1. So we not only modified K, this statement, when it finishes evaluating, not only has it defined and initialized K, but it has also modified I.
So once that statement's done, that's when we increment the I.
That's right.
Okay. Okay, that's what we get lost.
So there's a mnemonic. The plus plus comes after the variable. That means we do it later. Here the plus plus comes before the variable, so we do it
So
first.
then it gets switched to 2 before anything happens.
Actually, I switches to 2 before we use it in the statement.
Yeah. Okay. Okay, so that's what I was just getting lost.
7. You know, it's not very neat, but it's 7. So you need to practice those. That's going to be there. It'll be on the test. So something of that complexity. And basically, I'm just having you learn how to read code, basically, how to parse it, how to reason about it, in simple terms. Yeah.
Do we figure out which one's higher precedence, the plus plus I or the I? Does that necessarily matter? Like if you're trying to figure out a problem like this, that could be.
Wait, what was the question again? So,
what is the higher
precedence?
precedence of plus plus I versus like I plus plus?
A plus plus I is always done first.
Okay.
Very high precedence. I plus plus is always delayed till after the variable state is used. It's no longer has any effect on anything, and then you increment I. The table, I don't understand how to read that table when it comes to that plus plus. So I don't know why it listed the postfix as having a 1 precedence. I don't get that, but I think what that means is that, well, I'm not going to get into that, and that's getting too far, but this is a little confusing that the suffix or postfix increment is listed as having precedence 1. And I'm not prepared to explain that, but I have a hunch why that is. Yeah.
Could you do a postfix and a prefix and have one start off with it being positive and then two negatives at the end? So you can, change the variable to adding 1 and then change it at the end to being back to 0.
So something like, just read it out to me.
Yeah, so see how.
Go ahead. You'll see how.
Plus plus I minus minus, and then just the end line. With that, change the variable, and if you want to do another one, see out, and then to see if the I has changed at all. So it would increment.
I have never ever looked at this. Well, first of all, this will never happen in practice, right? Never.
Because it would first, in theory, it would first change it, display it, and then at the end it would change it back to where it was. So if you do another see out statement for I, then wouldn't I change, or would it not?
Based on this table I was looking at, I'm going to get, because this is weird, right? This is all that weird thing here. So let's all take guesses here. Okay, I'm going to think about this. I'm going to say that.
I think it breaks.
Oh, you think it doesn't compile, right?
So then,
So how many people think it
Do
doesn't
another
even
see out
compile? Huh?
do another see out so we can see how if it actually does it afterwards. So see out I at the very end of it.
Yeah. Oh, okay. Now, not just type it in and run it right now to see the answer. Okay, that's the wrong way to do it. You gotta test your reasoning first. Come up with a hypothesis,
So go back to the web.
then run it.
Go back to the web page. It says, let's see, it should do it left to right, so it should have positive as the first, the most precedence, we should be on the positive.
But wait a minute, the prefix increment is listed as having lower precedence than the suffix increment or decrement. So you don't have to worry about left to right or right to left, because it's the suffix decrement that has higher precedence. The suffix decrement has higher precedence than the prefix increment. I don't even know if this. First, let's just verify it compiles, and then we don't, because I don't want to do all the reasoning.
Okay.
I think it will compile.
So
It does not compile. Oh, it's not assignable. That's what it says. So it won't even accept this.
So you're gonna do one at a time.
Yeah. Yeah. Anyway, this is so, kind of off the wall example. You wouldn't see it, but you do. I got to tell you, you see this in code all the time.
Yes.
And tricky programmers use both forms, and it has important implications in code. So we got to know how to do it. It's not just C++. It's essentially every language. You take Java, JavaScript, C#, and Python. Does Python have post and prefix increments? Anybody know? I don't know. So it's kind of everywhere. So it's something you need to learn. Oh, I also want to talk about the following. The division. Let's look at division. There's two kinds of division, and it's confusing because the compiler uses the same, or the language uses the same symbol for two different types of division. There's integer division and floating point division. Unfortunately, they use the same symbol, so it becomes very confusing. It's a source of a lot of bugs, especially when you're just starting out. This is so important to remember this, that eventually you'll get it. But, all right, so we take, if we take I and divide by j, let's see what that produces. Of course, 0 divided by 0, that's illegal, right? So that's undefined. What does the code do with an undefined operation? Floating point exception 8. And let's suppose that's a 1 over 2. Okay. What does this print?
0.
Good. Got it. This is integer division. That prints 0.
What if you change one of the integers to a double?
Say that again?
What if you change one of the integers to a double?
Well, that's what I'm doing right now. Thank you. What does the second one print? Huh? 0.1, 0.5 rather. Right. So first we print a 0, and then we print 0.5. So this is 0, and 0.5 or 0.5, whatever it is. See that? It's the same symbol, but based on the context in which the symbol appears, the compiler will interpret it as integer division or floating point division.
Could you properly explain why 1 divided by 2, when they're both integers, means it's 0 and not 0.5?
Yeah, this is integer division, so that the result has to be an integer, okay?
Integers are whole numbers.
So if we use the double, we can put 5.
Yeah. Is everybody clear about that? If you take here, the compiler is saying I got an integer I'm dividing by an integer. This integer is 1, this integer is 2, because the compiler doesn't know that I takes on 1 and j takes on 2, okay? That's a runtime thing. But here, the compiler says, oh, you've got an integer divided by another integer. That means I'm going to produce an integer.
Okay, got it.
But the result is a half. The system says, well, that's not an integer, so let's make it an integer. How are we going to make it an integer? Well, a human might do some rounding. The computer doesn't round. It will truncate. It will drop the decimal, or the fractional component. It'll just give you the whole component, which would be 0. Is there a question? Yeah.
Okay, so in this case, on the second cout,
Yeah.
I is an integer and x is a floating.
Yeah.
Does that mean that if there's a floating point that's assigned, that it'll override and compute anytime that if there's any double or floating point?
Exactly. If there's
it'll do that?
any floating point value, the compiler will interpret the operation as floating point division. It's like the dominant trait, right? And being an integer is the recessive trait.
Okay.
Is there any way to lose it?
To what?
To lose it if you use a double down to an integer? Would that be a loss of any kind?
Yeah, we lose a half here, right? We're losing some information here. We're going from a double to an integer. We're losing the fractional part of the number. Now, how people do rounding is they do integer division and then they add. Actually, I don't want to do that right now. We already talked about that before, right? Here's another way to, let's suppose you don't have this x, you just have this. And you want it to print 0.5. Well, we can declare a double x and print that. So there's a number of ways of doing that. We could do this. We could say double x equals I divided by j. We could do that, and then print x. We can do that. That'll print 0.5. Oh no, it won't print 0.5. Sorry. Still print 0 because this produces a 0. And that 0 is then assigned to the x. So how do we get this thing to produce? How do we get? I want 0.5 here. How do we get 0.5 printed?
Wrappers?
Huh?
Wrappers or not wrappers? It's, that's for Java.
Yeah, that's right. Java. That's right.
Yeah, no,
You can cast.
typecast. Thank you.
Yeah. You can tell the compiler, hey, when you use j as a double here. That's called casting. So we're telling the compiler to just change its type in that expression to a double. Now it'll print 0.5. Check. What if we did this? What's that going to print?
0. They're still using J as an integer.
Well, let's look at it. There's two. Well, let's break it down into steps. It has to do two things. It's got to do a division, and it has to convert from integer to double. Does it do the cast operate? And that's called casting. Casting. When you cast, you cast an actor to a role in a movie, right? So this is the role you're trying to play. So we're casting this variable into another data type, or the whole expression. That's it. See, does a division evaluate first, followed by the cast operation, or do we cast I and then use that as the numerator in the division operation?
Second one.
You think so in other words, it's a question of precedence. Does the cast operation have higher or lower precedence than division? Well, I got to say, I don't know for sure. That's why I always do my cast. I would always cast J, because then I don't have to think about the precedence. But I would just, with all my years of experience, I would basically be guessing right now. Or we could check the table. Oh, this is function call. It's not casting. This is typecast right here. Typecast is this is its precedence level 2. All right, and then division. Where is division? Division is here. Precedence level 3. So casting has higher precedence. So you are correct in my analysis that we would first cast I to a floating point number, and then do the division. So the result would be 0.5. Anybody have a different idea on that? I got to tell you, this is only fun if you form a hypothesis before you do the experiment. Don't resist doing experiments without clearly formulating hypotheses. It's very important. You will not learn by just plugging in code and seeing what it does. Yeah, go ahead.
Like on an exam, are you gonna give us the precedence list, or do we need to memorize?
I will, well, I can't even remember it, okay? So I'm not going to expect you to remember it.
All right, cool.
If you wonder about the precedence of 2 operators or whatever, you can ask me in the exam. I will announce it to everybody. Okay?
So it's not open book?
No, but it's an open question. You're free to ask me anything, because I won't.
Anything.
I'm not obligated to answer all those. But
What's number 4?
all right, what should we do next? Is there any other part of this lab 2 that we need to take a look at before we move on to the material in the next lab? Yeah.
Can you do figure 4, please?
Figure 4.
In exercise 2.
Yeah. So this is not figure 3.
That's figure 3.
This one here?
Yeah.
Okay. So this one right here, I got it on the top. Let's take a look at this. When the code runs, what does it output? I'm going to just manually, it doesn't work when we copy and paste from the PDF, so.
It really doesn't.
Int I equals 11. Oh, look how convenient that is. Just add a little 1 there. And let's get rid of this. While I is less than or equal to 99. And then we have a loop. And my style is changing a little bit here. I'm using this. I'm putting the braces on the upper line, so I'm making things a little more compressed. You can do whatever you like, but be consistent within the context of a given program. I equals I plus 3. And then C out I. All right, so we start with I equal 11. And then we go into this loop with some condition, which starts as true and then becomes false eventually. When it becomes false, I is going to be some value, something bigger than 11. And we're going to print that value. All right. So we initialize I to 11, and we go into the loop. The loop condition 11 less than or equal to 99 is true, so we're going to go into here. And look, here we modify I. We add 3 to I. So the first time this runs, I becomes 14, and then it becomes 17, so on. And you better watch out, because I might do that on the exam. Okay, so now you can't do it manually. You have to reason about the code. Well, let's go back to the original. See, how many times does the loop run? Let's suppose the loop runs k times. Then at the end of the loop, I is going to end up equaling 11, which it started at, plus k3s. In other words, if the loop runs k times, we're going to add 3 k times. We just take k3s, k times 3. If the loop runs 10 times, we're going to add 3 10 times. That's adding 30, right? So, I'm just going to say, well, I is already 11, so how much more does I have to go up to hit 99? Well, let's see, if I take 99 minus 11, I get 88. Okay, so what's 3 into 88? What's 88 divided by 3? Well, let's see, 90 divided by 3 is what? 30.
29.
So 87 divided by 3 must be 29, right? So if k is 29, so let's see, if k is 29, then I would be 11 plus 29 times 3. And 29 times 3 is 87, because it's 90 minus 3. And that's, what is that, 98. So, 98 is one of the values that I becomes. If we add 29 threes to I, if the loop runs 29 times, we're going to add 29 threes. We're going to add 87 to I, so that I becomes 98. So just think for a moment that we're in the 29th execution of the loop. And I is now, after this statement runs, I is now 98. And then we come up to the loop condition, is I less than or equal to 99?
Yes.
It is. So we print 98. But that doesn't sound right. Is it 98? What did I do wrong?
Would it run one more time? Would it run one more time?
Oh, yeah. I made the same mistake. Half of you are going to make it the quiz on the exam.
Oh, wow.
Oh.
Confidence.
Can you believe it? This is not as easy as you think it is it? Oh. Yeah, now I got it now. Here's my mistake. When I became 98, the loop condition is true. That means we're going to do this again. And so now I becomes 101. Now the loop condition is false. So we go to the next statement and print I, which is 101. So now we're going to print 101. We got it, right? Any doubts? Okay. Let's make absolutely certain. We got it, 101 right there. I didn't, see out end line very nicely, but. I think that's a pretty, the analysis there is was tough. And you could actually do this if that was 99, but I want to warn you, what if that was 999? Then we gotta do it. Then we have to go through that reasoning process that we just went through. So, practice that. let's look at exam 1 here. You see, don't click show answer, okay? These problems are all very similar. How to analyze these loops. Here's a problem that has the, and this is a quiz I gave, or an exam I gave in the past. So these are problems right from a previous exam. Is there anything else in these set of exercises that you want to talk about?
I just had a quick clarification problem, like number 9.
Number 9.
Yeah. When we wanted to print out like good number or bad number, it's almost gonna be like number 10, right? Where we wanted to put out like even number or odd number.
Yeah. Write a program that prompts the user to enter a number between 3 and 12 inclusive. That means include the 3 and the 12. So we want the user to type in a 3, but not a 2. If the user enters a number inside, 312, so I use the mathematical notation, square brackets, to show inclusion. If the user enters a number in that range, the problem displays good number. The problem, it should be the program displays good number. Otherwise, the program displays bad number. So this problem here is different. This one here is a loop.
She said
Yeah, 10.
10, not 8.
Huh?
10.
I said it would be like
9 and
10.
10.
Oh, 10.
Wouldn't it?
Yeah, it's very similar to 10.
Okay.
Yeah.
Yeah.
Yeah, actually, yeah, it'll, like, there's an if condition there.
Yeah, because you could say like if, I is between 3 and 12, then Cout would be good number.
Exactly,
Right? And
exactly.
then if I is greater than 12, Cout would be bad number.
Exactly.
Okay.
Exactly.
What if they put a letter in there?
Yeah, if they put a letter in there, I think the system will interpret it as a 0. So it'll say bad number.
Yay.
I think, I'm not sure. All right. So everyone's okay with this other stuff, I assume, or you will be anyway. That's not that. Those last problems, those are not that tough actually. At the end there. Let's go to look at this one here. We only have a few minutes, so we're just going to start on this. If you have the lab 2 exercises already done, then you should be in this lab already. Okay, so it's,
Oh, I can't wait.
you need to get ahead as far as you can. It's much better to be ahead than behind. So-
Pass the class if I give you all the labs now?
Huh?
Do I pass the class if I just give you all the labs now?
Well, it's not enough points. You have to take the exams.
Alright. Just hang on, spend my weekend on it.
All right, detecting prime numbers. Listing prime numbers, factoring numbers, and generating random colors. So these are programs that are a little bigger than what we've seen so far. So far we've been just looking at really small pieces of code, trying to understand how if conditions work, Boolean expressions, greater than, that sort of thing. Oh, probably I want to talk about one other thing. I want to go back to that problem actually before I move on. Let's ask the user to input a number. This will be an integer, right? So we'll say integer. So let's put the logic in for saying bad number. There's a number of different ways of doing this. And I want to do it this way because I want to illustrate an example of a logical operator.
Quote. You need a quote. You need a good number.
What's that?
You need a quote at the beginning of the number.
Oh, thank you. Thank you very much. Save us a little time there. Let's start with this. See, I'm going to show you, this is just a technique. I want to make sure the code compiles and runs. So this is an expression. Remember, these expressions, these are Boolean expressions. So they evaluate to true or false. I'm just going to, tell the compiler it's always true. So this is an expression. The value true is this one of the two smallest possible expressions you can have. The other one being false. So this is always true. We're always going to say bad number. Let's see how that works. Enter an integer. And I'll say 12. It says bad number. All right, got it right. It says bad number. So it always comes up true. It's always a bad number. But what is the expression that we use that evaluates to true when n is a bad number? What does the expression look like? Well,
N is less than 5.
n is less than 5.
Or n is greater than 9.
What was before that? N is less than 5.
Or n is greater than 9.
Or
I don't know if
n
this
is greater than 9.
Can you use the word
It's
or?
equal to false.
Well, we'd like to use or, but it's not defined. We have to use a symbol for or.
Wouldn't it be better to define good numbers since there are fewer, like the range of good numbers is in between 5 and 9, whereas it would be easier to write that expression.
Well, let's do it that way as well. We'll compare the differences. How do you do or?
Shift and then that one downward slash twice.
That's it.
Is that right?
I believe so.
Let's go to the precedence table here. This table contains all of the operators in the language.
Straight up and down.
Logical.
See that one right there? Bitwise or. All right? And compare that to this one right there. Logical or. Bitwise or, logical or. Which one do we want?
Logical.
We want logical or. And we're not going to talk about bitwise operations in this quarter. We'll talk, if you take Computer Science 2, we'll cover that next quarter. Okay, but this quarter, we're only using the logical operators. So it's this, whatever that symbol is called, right?
I'm great.
That's the or operation, logical or. So if n is less than 5 or n is greater than 9, in that case, we're going to say bad number. So 12 is a bad number. It says bad number, good. How about minus 9? Bad number. What did you say, 0? That's good. That's a good number. That's a very good number to try.
7.
How about 5?
What about D?
What's 7? 5.
Let's try D.
Let's try a letter.
Yeah, what happened to do a letter?
11?
A letter.
Yeah, like D.
Oh, a letter.
It means bad.
Well, this is not a case. Now, here we should have extra code that tests that the user has inputted a valid number. I think it treats it as a 0.
Doesn't it treat it to the ASCII, or is it ASCII, or it's one of the? Because there's a way of representing it, isn't there?
Yeah.
where it's like 0 through 26 or something like that, A through Z?
It doesn't interpret as an ASCII because it tries to convert the letter to a number. I'm not sure exactly what it's doing here. It's trying to convert the input into a number, and instead of reporting an error, it let me. I should answer this. Let me
Try
dig in.
F, because it's within 5 to 7.
Watch this. There's this input stream has got a state, and I think it's in, is it fail, something like that? I'm not sure. We'll have to look up the documentation. Oh, bad input. What do you know? Yeah, I'd like to take a nap right now. So bad input. There we go. I'm just guessing here. This is an object. It represents the standard input stream, and it has a state. Like everything is okay, and then if something is wrong, internally it says, "Oh, I'm in an error state." I'm not sure that this is the right.
Did you compile it?
What did I say? I said bad input, didn't I?
You didn't compile.
I didn't
You
compile it.
compiled it.
Thank you for catching that. Well, that's not it. It's ink, isn't it? B. Bad input, see?
And bad number.
Yeah, so, but that's,
Because it's
it didn't actually set n to anything.
Yeah.
N is in random because it never modifies n. It just, so we would have to check this first
You can
before
just
before this makes any
set,
sense.
if you did the fail, then you can just set, if that
Could you try
is
G?
equal to true, then you can set n equal to 0.
I better we do this. See that? So if Cn failed, then we say bad input, else it's a good input, and we give our response. And you see how I'm indenting to show inclusion. I want to tell you, remind everybody, I'm only talking about this in lab, but you need to use indents to show the logical structure of your code. So generally, if you've got a statement and it's a substatement within another statement, it should be indented. This is an if statement. It starts here and it ends there. That's one statement. It's a compound statement. It has two substatements in it. That's a substatement, that's a substatement. This is called an expression. And it's the condition. This whole thing is one statement, and this is a substatement under, in this larger if statement. This is a single statement right here. It starts there and it ends there. And this statement has two substatements. That's one substatement. And then this is another substatement. Of course, that substatement itself has a substatement. And so each of that subbing, you see an indent to express that hierarchy. Got it? Okay. What about 4.4?
Hold on now.
Because I'm saying read an integer. I think it stops when it gets to the period, and it considers it a 4. See, it doesn't say bad input, it says bad number. But if I did 6.4, it'll say good number. Because it's parsing, and what it does is it starts, when you do C in N, right here, the program starts reading in digits until it gets to a non-digit. If it gets to something that couldn't be part of an integer, it says, oh, that's enough. I'll let the next piece of code process the rest of that. So normally you would reach a space or would reach a new line, which is what happens when we hit enter. We generate a new line character. And so it's looking for what's called a delimiter. So it's scanning the input stream, and if it finds a digit, it says, okay, I've got that digit, I'll get the next one, and I'll get the next one, and I'll get the next one. And as soon as it gets to something that couldn't be part of the integer, like a dot, a period, or a space, or a new line. But, this is a topic that I used to get into. I used to cover this, when I taught this class a long time ago, and I think it's a kind of a minor topic. I mean, you have to, if you write command line programs, you've got to know this stuff, but, most programs are not command line programs. And the most important thing, in my view, that you need to learn right now is how to understand loops and conditions, how to get a statement and develop the algorithm to solve a computing problem, not to know these kind of little details about how the input stream is read and all that, although that is important, of course. I'm trying to focus on the most important part. I think that's enough for today. I won't go on till after in our next session, I'll start the problems.